char string. Now I'm waiting to see if Google pick it up. All right, I think Google pick it up. All right, it is January 30th. All right, it's kind of late today because I had a lot of other things to do today, but we'll always go through the daily LeetCode challenge. Let's get over some of the issues we had yesterday. Okay, so this is what we have yesterday. We solved it, but eventually I got stumbled upon the implementation of heap queue in Python using a custom class. So I'm just going to pull up the code that's relevant. So this is going to be the code. Oh, actually, it's right here. Oh, I didn't see it. All right, it's right here. So this is the correct code. Let's look at here. So I implemented this part yesterday initially, and I was like, it just didn't work. Like, why? Why did this code not work? I mean, we have to implement a Thunder magic method called LT less than. So this will be the function that the class will be called when heap queue trying to order, right? So you guys look at here. This is the class we implement. It's called wrapper, and in wrapper we have to implement this Thunder LT function such that when we push this wrapper into heap queue, well, not really into heap queue, into a queue, into a list, and a heap queue tries to do the heap magic. When it's done doing that, it uses this function to compare two different wrappers. So we need to basically tell heap queue how the wrappers are ordered. So the idea is, I say we're gonna compare on the x coordinate first. So the order is the smaller x coordinate things goes first, and if the x coordinates are the same, then we're gonna order based on y coordinates. The bigger one goes first, and if the y coordinates are the same, then we compare on the value. And the smallest value goes first. So here is my initial wrong implementation. I say I'm going to compare on the x value first. I say if x is smaller to the other one's x, then we return true. This is correct, right? Because if the current wrapper's x coordinate is smaller than the other one, then it should go first, which is true. However, the problem is if it is not. Like say if f self.x is larger than other.x, what we should return is false, because we can make a comparison based on x. But in this case, if self.x is larger than other.x, then we go directly into comparing the y. So this is not correct, because we still can distinguish the two wrappers based on x. We don't have to look into y. And the only time we need to look into y is when the x are the same. So this condition is not correct. The condition should be to check whether the x are the same. So now look at the correct code here, which is also implemented here. This is the same. So look at the correct code. We first check if the x and the other x are the same, right? If they're not the same, then we return the comparison, the natural comparison between the x. And if they are the same, then we need to check on the y. And following the same logic, when we check on y, we see if the y are the same. If the y is not the same, then naturally we can return not the natural ordering of the y, because we want it to be the larger y's will go first. So instead of self.y smaller than x.y, we actually go larger. So finally, yeah, so that's actually correct. So finally, if they're the same, if self.y is equal to other.y, then we compare on the value, and then the smaller value goes first. So this is the logic for the Thunder LT method. And if we put in here, it works. This method works. The runtime, it's similar to others. There's no major improvements, but the main ideal of this one is we can use a priority queue or a heap queue to do the ordering. And the magic is here, right? We do the ordering for us, and all we need to do is we DFS or EFS doesn't matter. We go through every node and we push the node into the priority queue, and then when we want to process it, we just pop it out. Now, there's a little bit of logic here, like when we pop the things out from the priority queue, how do we determine when to add the popped out value into a list and into the, we want to return a list of lists. So when do we add it into the internal list, and when the internal list needs to be added to the main list? But this relatively is easy, and I don't want to go through that anymore. So this is just a wrap up of what we encountered yesterday. All right, now let's go to today. Oh, I just think I need to go back. I'm back. Come on, back. There we go. This is the Explore on January. Oh, one more time. All right. Before, let's take a look if there's anything I need to pay attention to. I don't think so. I don't remember when I do those. We don't need this anymore, so we're gonna close it. All right, let's see. What do we have today? Minimize deviation in the array. All right. Usually the challenge on weekends are pretty hard and kind of late. My brain is like half shut down right now, so there's a high chance that I won't be able to solve this. But never say you can't do anything. You just try it first. Let's see. Minimize deviation in an array. You're given an array nums of n positive integers. Okay, we're dealing with positive integers. You can perform two types of operations on any element of the array any number of times. So any element, any number of times. If the element is even, divided by 2. For example, blah, blah, blah. I can do this operation on the last element. Okay, means I can do it again and do it again. If the element is odd, then we'll multiply by 2. So we multiply by 2. Good. And the deviation of the array is the maximum difference between any two elements in the array. Return the minimum deviation the array can have after performing some number of operations. For instance, in this one, you can transform the array 1, 2, 3, 4 into 2, 2, 3, 2. So it's basically times 2 divided by 2, so the difference is 1. You can transform 2 operations, and then the max is 3. And this one, I suppose, times 2 times 2. Why is it 3? Times 2 is 4 times 2. It should be 2. Huh? Oh, well, this is positive. This is even. We cannot multiply, can only divide. So, oh yeah, if you divide it and then you multiply, divide, multiply, then this. So the even number only have 2 ways to go, right? If it's an even number, oh no, I mean odd. If it's an odd number, we multiply by 2, and then there's nothing more we can do, and then it becomes an even number, and the only thing we can do is divide it by 2 and then go back to the original. So if you are why I keep saying even, it's odd. If you're an odd number, then only thing you can do is either double or stay the same. Double or stay the same. That's only 2 states. But if you are a even number, you can go down. So this one goes down. It becomes 5. So this is the same. 5, 10, 5, 10. This one is a bit different. This one can go down. So it's 8, 4, 2, 1. So 1, 2, 4, 8. So I think for each number, for each position, we have a finite number of states that it can be in. Let's just take the last example, 2, 10, 8. So the last example, the first digit, the first position, we can have 2 or 1. The second one will be 10 or 5. We cannot have anything else. And the third one will be 8, 4, 2, 1. We'll have 4 values. So basically, among these, we need to choose a configuration that has the minimum value of the maximum difference between numbers, which means we want the values to be, we want a big kind of value to be small, we want a small value to kind of be big. So in this case, we see that the, how do we find it? So the first position, right, we can choose 1, and then the second we can have 10 and 5, and we won't have 10 because that's 10. Why do we not have 10? So it doesn't matter. But I'm just thinking about like what we're trying to do now is that a DFS? Would DFS be a better approach than say DFS? It's like I'm picking 2, right? And then I can pick 10, and then I need to pick something that's so we set it 8. Now we're gonna pick something that's basically smaller than 8, and then the largest is anyone is smaller than not anyone is smaller than 8. So we can pick one. So we can now is 8, and then so we set here, right? And we just see if we can maintain. So we know on this path it's going to be, and then we only need to do, because okay, so we don't have to look through everyone. So we look at the biggest one, and then the biggest one is smaller. Now because the biggest one is smaller, okay, I need to show you guys what I was thinking about right now. Otherwise it's kind of a moot point. Alright, let's see. This is what I'm thinking about in the last one, right? So for 2, 10, 8. For the first position, we have 2 or 1, right? For the second position, we have 10 or 5. And for the third position, we have 8. Here, 4, and 2, and 1, right? So this is what we have right now. So my thinking is doing a DFS. So we start at 2, we go to 10, and so every time when we go, we find, right? Because we go from top down, which means we want to go from the largest to smallest. So say I pick 2, and then I pick the next one, I should pick. So every time I need to pick one that has the smaller, it's not going to be 10, it's going to be any one that is smaller. How do we know? I mean, it is not possible to directly know, so we have to search through the space, which I really don't want to search. It feels not right if you search. Now if you don't search, you go to 10, right? And then, but you don't search, it has to go through everyone. So you know that some will be better than the others. So like I know that 5 will perform better than 10. It's just like for a fact, right? So I know, which means we can do a binary search because this is ordered. We can do a binary search and find the one that's the closest. So if I do binary search here, it will be inserted here. So we say it's going to be 5. So this one will be 5. Now we're looking at 3. So we want to see binary search. Binary search, the closest will be here. So the closest will be 4. So we do this. So this gives us 3. Right? So that's the path. That actually is the smallest path. Given that's the smallest path. Indeed, that is the smallest path. Given the first one is 2. That is the smallest path. So we're going to try another one. Start with 1. Binary search tells us we're going to go 5 and 4. Boom, we're already down. So we're done. Alright, let's try another one. Let's try 4, 1, 5, 20, and 2. So we have 2, 1, that's 4. 1, let's just order it. 1, 2. Next position, 1, 2. Next position, 5, 10. Next position, let's see, 5. Let's do one more. 5, 10, and 20. Right, because 20, we can only divide to 10, can only divide to 5. And the last one will be 3, and multiply will be 6. So that's how it looks like. The same thing, we start with 1, binary search will give us 1, binary search will give us 5, this gives us 4, binary search give us 5, binary search give us 6. So this ultimately give us 4. Or we will start with 2, binary search give us 2, binary search give us 5, binary search give us 5, 6. This output is 3, which is the answer. And what we see here, we have repetitions. So we can do a cache. Every time we hit a position, if the value in this position has been checked before, we need to record. This is basically going to be at each one, at each position. So we can do at each position, it's going to be a dictionary at each position, and I'm going to put a key will be this. So we just at this position and check if this value has been examined before, if it has been examined before. So for example, this one I examined before. So from this one, so basically we want to select from this one going on. Well, we want to know what's the value. Oh, we can go it the other way around. Is this dynamic programming, huh? We go from this position first. So we know 5. From 5, the least will be 1. From 10, the least will be 4. From 20, hold on. We just want to know if it is possible. So if 5 can give us, I mean the last one, this one has no say, right? This one has no say. So we start from this position. 5 we have a 1, right? This position 5 we have a 1, and this we have, so this position is going to be a 1, and then we look at this position. So this position, we check, is going to be 0, and this position is going to be 0. So from this position is going to be 1. Hold on, no. We already determined that this position has to be 5. Why is that? Why do you think the best in here can be applied for others? If we do 5, would it be possible that if we have a bigger one here and the overall will be smaller? Say we say 10. 10 is better than 5. What type of scenario would 10 be better than 5? Yeah, say everything else is 10. Yep, say I have a 10 and 10, 10, 6. That was 4. But if I have 10 and 10, 5, 6, then it'll be 5. So no, you don't know. You do not know. So have to check everyone, which means on n log n. You have to check every single one of them, and then you produce a value. So we have a value for here, so we know this one is 1, So 5 is 1, 10 is 4, 20 is 14. Now we check here, 5. Let's find it. So it's going to be copy this. So this will be 1. This will go here. So this will be 4. And this will be 4. And this will be 3. And then in this one, this will be 4. This will be 3. So eventually, we look at this. We pick the one with the smaller. I'm not sure which one will actually give us the better, but I'm going to go with this. Feels to me a bottom-up dynamic programming with binary search when you want to find, when you want to find the best option at each position. All right, let's take a crack. Yeah, let's get a little bit bigger. Let's be bold. Okay. All right, so what we need to know, if it's an even number, we divide. If it's an odd number, so we can give, it's going to be an array of array. We're going to start with num list equals this, and then for n in num, if n divided 2 is the odd number, then equals, actually don't have to. I just go num list dot n. It's gonna be n and 2 times n. Else, even number. While n divided 2 equals 0. And it's an even number. Then you need to reverse it. Huh. Okay, does reverse? Okay, next up. No, we need 10. 10 equals this. Can you have a better way to do this? 10 dot append and 2. And then we say num list dot append reverse sequence temp. Probably has a listed. I'm not quite sure. I want to check it. Simple thing. No, just to check. Just I need to 1, 2, 3, 4, 5. If I call reverse, what's gonna happen? Oh, it's gonna be a literature, so I cannot see. So I have to. Oh, I remember what I can do. Dummy. I like the other way better. Actually, want a fancy way? I need to make sure it's make a copy. All right, so we create this, and then we need a we'll call it dp equals this, and 0 times L for L. No, I said it not. For NL for NL in num list. Alright, that's what I'm talking about. And alright, I'm not quite sure if it's correct, so I want to want to double check if there's any error we can just find right now. Let's do one example. Oh, no, I don't. This one is we can test on both eventually, sure, but this one will give us a clear view of how things work. So we just gonna this, and then we are going to print. I want to print num list, and I want to print DT. Just double check. No, just double check. All right, num list. Oh, that's not right. Right, it's not right. So then it's 1. We need to append the 1 as well. So we need to append and when it's even number as well. Odd number. Kept saying even number. Right? So we have 1, 2, 4. Oh, it's 1, 2, 4. That is correct. It's 1, 2, 4. 1, 2, 5, 10. 2, 10, 20. Yep. I think we're on the right track. Now we need import by set. All right, we're gonna go from the right mode. So we're gonna say for I in range len num list -1, okay, -1. Okay, so actually it is -2 because I don't need -1. And okay, current list equals num list I, right? So we're not looking at this one. And then we say for n, j, and enumerate. I can save one. Okay, this is necessary. So we're iterating through these, and we get 5 out, and we need to find. So we can say doesn't really matter. Lots of bisector, right? So we always need to check on both. So if it's in the center, well, not in the center, it's always like if I want to insert it between these, if it's bigger than this, smaller than this, insert, it's only going to be like in the front. So we're going to go bisect left. So I'm going to say position equals bisect left. And put a sequence in. Sequence will be num list I plus 1, which is this one, and the value is going to be n. Right. So let's find this out, and then we need to know where does it fit. Right. So if position is 0, which means it's inserted in the front, so we can do dpi dpi j equals abs n minus num list I plus 1 0. Alright, if the list position is len this, make a way insert the end, then we do equals minus 1, because it's at the end, right? It's at the end, so we do -1. Else, that means it's in the center. If it's in the center, then this equals this minus. So it's gonna be position, right? So we can insert. So it's gonna be insert here. So it's position, which means this one, and also position -1. Yeah, on the position minus 1. So we're going to be abs this, position minus 1, and we pick the mean between them. We might be able to like optimize this, but I don't see the necessity for now. I mean, if you think about it, if position is 0, right? Position is 0, and this is 0, and this is going to be minus 1, which is far away. So that one will definitely be larger. So this actually can be covered by this. If it's like the largest, then position minus 1 is the front, and current position, oh, that will actually raise an error. So we can eliminate this. I think we don't need to check on position goes 0, because position goes 0 can be covered. So I think the only thing we need to check is this. So we do that for each value, and after we're done, we move on. That's actually not true. That's actually not true, because we need to compare. So this is the difference, right? The absolute difference, and we need to compare this with dt I plus 1. I plus 1 what? So if it's the last one, right? So the position is the last one. So we pick is minus 1. So it's minus 1. So we need to compare to this, and then we pick the mean out of these two. And this one is the same. So it's gonna be, oh man, it's gonna be a lot of things going on. So this is the mean of the current thing, right? Or which one we use, right? And then this is actually not mean, this actually is max. And for this one, mean of this and dp I plus 1, and we chose, oh man, holy smokes, I need to know which one we choose. So we have a position, then we have position itself for position minus 1, and we need to know which one is closer. So we say if, man, this is not how I imagine it to be. If abs, actually, fine. Diff left equals this. Yeah, I think it's explicit is better. Diff right is, I think I got it wrong, because this is actually left. This is actually right. So we have diff left, diff right, and then we say if diff left is, or what if they're the same? Ooh, if they're the same, then we have to, okay, if this one's smaller than diff left, so to make this one is smaller, then we're going to pick diff left, so dp I j shall be the max of diff right and dp I plus 1 position. Now let's diff right larger than diff left, then the same thing, but we're going to change to position minus 1, and this is going to be diff left. And finally else, if they're the same, then dpij equals max diff, doesn't matter, let's choose left, and then it's going to be, how do you say do? gonna focus. It's gonna be the mean of dp. Yeah, mean of dp this and dp this. Right, so for each value we check the bisect on this, and then based on the position we do all these crap. A lot of crap going on, that's for sure. Then after we finish, we fill in the dp, and then we go keep going until we finish it at 0, and we exit. Once we exit, we have the I value, so we know that dp. So what we want to return is the mean of dp0. The mean of dp0. Alright? Oh, yeah, I tried to run it and then immediately find problem. It says this assignment index out of range. How is index out of range? Alright, we need to do some debugging. So we start from numless. We start from not -1, -2, which allows us to do I plus 1. And then position. Right? Position is I plus 1 is a list, and I have current n in it. Right? I have current n in it, so we kind of see where the position is. I mean, say the position if it's equal to the length, that means it's at the end. So we cannot, and then this already says the position is not at the end. The position is at the front. So the position is at 0, right? So the 0 or -1. So ideally the difference will be bigger than this. So this r is smaller than this left. So we say dpi j equals the max side of this right, and then dp I plus 1 and position. Alright, I don't know. We need to run a little another magic here. Python 3. What is that? 30. Alright, let's debug it. Oh, we're gonna run this. Enter. Let's see. This is our num list. Yeah, actually, let me see this num. Find num. Temp. It doesn't matter. So for dp, have it. So now I is 3 because we have oh, that's not what we're supposed to see, guys. We have 0, 1, 2, 3. Yes, that's right. So 3, and then let's keep going. It's 3 and then 5. And it's 5. It's 3 and then 5. Yeah, so that's 5, 10, and 20. Yep. And then position is 5. Position is 0. Position is 0. No, wait, position is not 0. Position is 0. N is 0. Oh, shoot. You see the error? There we go. Because enumerate the index so first. Alright, try the other test case. One, two, 10, 6. Pass all. Alright, I don't even know any other test cases. Give me some. And is at least 2 numbers, 2, so that's just a 2. Can I do, oh, no, 1, 1? Like the edge of the edge case. Okay. 2, 1. I'll take this advantage. I'm gonna do random import random, and then we're gonna do random 1 to 10 to 9. Jesus. Man, what happened to my typing today? 10 to the 5th. Maybe I'm confused for a while. I'll let it compute. We can set 0. Can't cover everything. That's fine. Let's cover this. See if it runs. Ooh, that's not correct. Huh. Alright, let's see. It seems like we have an issue. That's fine. Let's just generate a random number. Of course, we do 5, 10, so that's crazy. I don't know why. I can't copy it. 2, 8. Hey, correct. Oh. Yeah, we're gonna hunt down. Yeah, what went wrong? Oh. I don't know. Just trying things. I don't know. Oh. Oh. Nope. I'm trying to find a test case that is small enough that I can work with and evaluate what actually went wrong. So that's good enough. Alright, that's good enough. Let's take a look. I mean, this is good about LeetCode, so you can actually find error. Imagine you're doing this on, say, HackerRank, and you don't even know how you were wrong. Well, in that case, we will employ a solution that's very different. We will do yeah, I will show you guys once we get there. Yeah, we have this error. Hey, think to analyze this, we first need to print the numlet for sure. See if the numlet is correct. So we have this. We'll be divide 12, 6, 3, 4, 2, 1, 1.2. So the result is 35, but I got 36. Let's see. So 21, 4, and then 12, and then 39. 39 minus 4 is 35. How come I got 36? That is weird. That is weird. So we're gonna just check on we're gonna check on what are we gonna check on? Let me just print the CT and just say how each step goes. Alright, first is all here, no problem. Second level, we're probably gonna print DP at the end as well. Why don't you just print DP at the end? So we're gonna print DP here before we start, and we also print DP at the end when we finish level. Right? So started here, 3 is from 36, 6 find 33, 12 from 27. That's correct. Second level, 1, we're gonna go to 3, that's 36. Oh, before I go to 3, the 3 is 36, but actually 4 can reach a even smaller one. So are you saying that we need to record something else, not just the smallest? Yeah, so we have the smallest. We know that from here, the smallest is going to this one. And if we go from 3, because all of these are attaching to 3. That's correct. We need to find the one that is from this going forward, the smallest. And then from the smallest, we can find this, the smallest difference. But it is possible that for the numbers here, when we get the smallest, we need to know that if this one needs to get updated. And how do we know it's going to get updated based on this level? What if we have many levels? Right? Imagine Yeah, imagine if I have like a really large number here, a really small number here, and a really large number here. And then with a small number here, right? With a small number here, what we have is a big difference. And with this, we'll have, but hold on. So like 3 is 36, right? And then we give 4, it should still be 36. Ah, I see. 4 is not going through 3. 4 is going through 6. 4 goes through 6. 6 give us 33. So if 4 goes through 6, and 6 has 33, and 4 has 35. Oh, this is more complicated than I expected. Is it not DP? Because it's not completely dependent on this. It also depends on how the current value interacts with all the values behind. I mean, DP might not work. Yeah, because the state, so that when we consider 4, right, the state in 3, 6, and 12 cannot. We're going to have to do it the other way around. How about we go from front down? So 21, we will seek for 4. And then 4, we will seek the same. 4 will seek 3. 3 will seek 39. They give 36. 4 will not seek 6. Because it's 4, so the smallest is 3, right? I won't go to 6. But if I don't go 6, I cannot get. Ooh. Yeah, the minimum is actually I can remove 21. 21 doesn't really matter. This is the minimum. This is the minimum. I can demonstrate the error. Yep. So start from 4, right? So we can go 3, and then usually we go the smallest. The problem is from 4 we only go 3, we don't go 6. Even if we go both, it's not going to be correct. So like we go 3, then we get 36, and I decided I'll go 6 as well. And if I go 6, I'll get 33, which is also not correct. We go both. Think about it. We're here. We have 2 choices on both sides, right? And any number outside is not going to be. I'm not sure. Okay, so say this, we have a value, right? And so I'm bigger than this, so we can compute the value. So I am bigger than you, and then you have a difference. Or you have a difference, and if the difference is bigger, then it overshadows me. But I can also, based on the difference, to know. I'm just afraid, like if there's something like hidden really deep. Hmm. So like say every one is correct, and you hit me, right? So we go layer by layer. And each layer I'm correct. The first layer is always correct. There's just no question. The second layer, right? The second layer, how do we make sure it's correct? So we compare it to we find the adjacent, the two values that's adjacent. Right? Find the two values that's adjacent, and we decide that we have this one or we have this one, and we compare to the so if we have like it's a tuple, so we have the value and we also have the number that we want to pick based on this. So I have the number that we will pick, and now we have this. We have 4. Right? We have 4. To say we not only we don't record um we don't record the actual value, but we record which one we pick. So for 3, we're going to put in here is going to be 39. So for 3, we say we pick 39. For 6, we pick 39. For 12, we pick 39 as well. And now we go to 4. And 4 is in between. So we can choose this or choose this and choose both sides. And we see if we choose 3, we know this is going to be 1. 23 will be 1, and then we also see which one. So we're going to say the main difference is going to be dominated by 39. So 4 and 39, so this one will be 39 as well. And then, so if 4 is 39, which means 4 is in the hand of 39, and then when we do 2 with all these, and 2 and 3, so 2 is going to be 49. Well, 1 is 49. So eventually, it's going to be 39. 4 and 39. That will be the final result, which will be correct. So we are actually recording the value that results in the current maximum difference. Will this work? Because if, like, we choose this, right? Why don't we do 12? I mean, we can do 12, but then 12 is a bigger, we result in bigger value, right? We result in bigger value. So we can pick 3, but if we pick 3, then it's going to be 39. So it's going to be 36. We have to maintain 36. So pick 3 is going to be 36. 6 is going to be 33. Because this doesn't matter. Are you saying we just we have to go through every one of them? For each value, we have to go through every one of them and just see which one has the, like, say it's 4, right? We know that it's going to be dominated by this instead of, I don't know, man. This doesn't seem to be the right way forward. And this level is correct. Right, so choose the one that's closest to you. It's on this level. On this level, we'll compare sort. So this is the original value. We know the biggest is at the end, right? So for each one, we kind of need to see which one to pick. So I pick 3, I pick 6. Why only pick these two? Why don't we pick 12? And then is it likely that 12 will work better? Maybe 12 will work better. So I turn 4, and pick 12. I am generating 8. And then basically in this situation, whichever you pick, it doesn't matter because it's dominated by this one. It's been dominated by this one. It's been dominated. Which means all of these are picking the same value. Which means no matter which one you pick, it doesn't really matter. It's going to be, so all of these, so you go here, you're going to go here no matter what. So you will have to, so you go here, it's going to go here. If you go here, it's going to go here. And if you go anyone, it's going to go to the same. So it's been dominated by a value. If you're dominated by a value, then that means if we sort it from small to big, then for each layer, it's going to look at the next layer. And if the next layer all pick the same value, then you have to compare it to the big value. Because so we have a layer, and all of the values in this layer, they pick the same value, right? They pick the same value to go through. So essentially, in this layer, we have this value and this value, because if this is bigger, like if this value is bigger than all of these values, and this value is dominant. No, I think this thought process is not correct. It cannot be. Too complicated. It doesn't feel natural. I'm writing it down to get some of my intuition. So what we want is the difference. And we want the difference to be the smallest. Meaning this node, we have value, it's 2. This node and this node has value, right? This node and this node. So they can all connect it. And the idea is to take from this node, we want to go to, so we don't want to go to this node. And I don't want to go to this node. Because if I go to this node, it will be more expensive than go to this node. But it's actually you don't know. You don't know. Basically, so it's like this. It's like neural networks. We're saying find a path that will result in the smallest. So like say we can start with 1. And then the curve will be 2, then it will be 5, 11, and then we'll take this one out. We don't come back. And then we will go to this. Well, if we do this, we already solved the problem. Issue is from the middle layer, everyone will pick this, so that's the is the smallest difference. Now from the front layer, the first layer, from the first layer, we have issue because one, we pick this, and we pick this, right? Let's say one pick this. So basically, what I'm saying is, if so, we know this the difference is 36. This difference is 33, and this difference is 27. So these are gigantic differences. I have gigantic differences. And then when we see here, we can actually do a min and max, right? So okay, so the mean difference is 2, max difference. Oh, you don't know the mean difference is 2. We know the mean difference by comparison, so we know the mean difference is 2. And the maximum difference is either min or max, so the max difference is 11. So whichever way you choose, you will see that it's been dominated by these values. So you shall choose a one that so we know that 3 chooses 39, 6 also chooses 39, 12 chooses 39. So for 1, do this, and then we know that we choose 39, so we go here, we choose 39, so we know this one's actually 38, right? That's 38. But you actually have to compare every single one, because it could be that this one chooses, yeah, say like this is bigger. So instead of 12, this is a little bit bigger. If it's a little bit bigger, then if this is a little bit bigger, then I can choose other value. Say like not 39, but the point is this cannot choose the smallest. You're gonna miss. You will miss. Hmm. Another thing to consider is start is 1 and 4. This is 3 and 12. This is 39, 3 and 12. Right, this is the range. In order to make it smaller, if we choose the smaller here, and we choose the smaller and we choose smaller, or we choose the larger, then this one we choose the smaller, and this one we choose the smaller or the larger, so we choose smaller. Or we can see one. So we're 1 to 4 at the start, and then now the second one is 3 to 12, and the last one is here, 39 to 12. So I want to pick one of the numbers, right? And in this situation, the best is only 1 and 4. So here, If it pick the low end, but if it's overlapping, right, then the small will be yeah, this is a hard problem. If DP doesn't work, I think DP will work. This I wasn't able to figure out. It's a little bit trick in there. Like what else to consider in DP? Like this layer is easy, but in this layer, let's jump out. Let's just go to another example. Let's kind of, I mean, these examples, you have to make this one work. Well, if I attach it with me, the value that I'm going to choose, then it still needs, well, why don't you check 12? That's a very legitimate question. Why don't you check 12? Well, because I don't have to. This 4 is in between 3 and 6. And choose 3 because 3 is the best option. But apparently it is not. Because if you choose 3, so incur 36. If I don't even know it's 36, I mean, I do know 36. Because I know from 3 it's going to be 36. And from 6 it's also it's 33. Yeah, from 3 is 36, and 6 is 33. So it shouldn't be you choose the one with the lead. Now we know this is 36, this is 33, this is 27, so you're supposed to choose the one with the smallest. Alright? You choose the one with the smallest. You choose the one with the smallest, so this one has the smallest difference, which is 27. So you choose that, and then we can consider your difference. Right? So if your difference is smaller than this difference, then if your difference to this value is smaller to the difference between this value and the next value, that means, well, it doesn't mean the next value will be bigger. I mean, you have to attach it. You have to attach it, right? You have to know that which one you actually choose. So say you attach it, so you know which value actually gets you this difference. So the maximum difference so far, yeah, this one is the maximum difference so far from this one, from this going forward. The minimum, the mean of the maximum difference. The mean of maximum difference is 27, and it is going to be, you know, a positive number. Doesn't matter if it's a positive number, but just like it's a difference, right? It's a difference. Okay, no. It's like after 4, after what we're going to do. Maximum difference is going to be based on 4 and this, because there's a maximum difference is this, it's going to be 27, and then there's a smaller maximum difference, and we compare these two, and we found these two, the difference is smaller than this, so it will be dominated by this. So we also need to compare this with the value that is causing the maximum difference. Right? The maximum difference will be the biggest value and the smallest value. Right? The biggest value and the smallest value. The pair. Yeah, the pair. The pair that creates the maximum difference. We record the pair. And here we record the pair. And we know that in this pair it is 27, that's the maximum difference. And now we have this value, we're going to compare with this value first. Right? No difference in it. And then we use that, we're going to compare if this is smaller than the difference in this, then the difference is dominated by the previous one. And you're adding to it, so you're going to compare U to the current pair. And we're going to update. So update to 4 and 39. Right, 4 and 39. And then we're going to go. So the situation is if you're smaller, like you do this and then basically the range, right? So the range from this one moving on. The range from this one moving on is this. And you add a new number to it, and you find that if you're in between, then the range does not change. Right? So if like we have a bigger value, then the range does not change. It only changes the range if it's smaller than the range, or if it's bigger than the range. The same thing with and you always pick the smallest. Yeah, I think it might still work. Let me work on another example, and also kind of see if sorting is really important. I don't really think sorting is important. So 1, 2, 4. This is going to be 1, 2. This is going to be 5 and 10. It's going to be 5, 10, 20, and 3 and 6. So we are working on this one again. Just change the mindset. So again, from 5, we're looking at these two. We pick the one that has so this one will be attached to, this one will be like 3, 3, 6, 6. So 5 coming in. These two are the same. So we're going to do both. Like if there's no smaller. I also have to find a smaller. So the smallest, how do you even find the smallest? Suppose we can find it. So here, if we want to update it, it's going to be 3, 5. With this, it's going to be 5, 6. So this one's going to be 5, 6. I mean, this level we can actually do by the same thing we did before. So this one is 6 and 10. This one is 6 and 20. Right? So this is the range. Now we're going to change and check from this to all these. So how do we check? So the difference between these is 1, 4, and 14. So we choose the one with the smallest, because if we choose the one with a little bit bigger, then we know that we will incur more. But it is possible that if we choose one with smaller, if we choose one with smaller, but you're saying that we have to check every single one of them, right? If you run it, and then we update it to the size 6, and then we run this, so if it's bigger, so basically we are going to check. So we do binary search first. So binary search, we'll find it, and then we check. So this is going to be, so we find a binary search, that is going to lead the same range. And then we look for the next one. Alright, look for the next one and see how the difference changes. So next one, this one gives us difference 4, but this one gives us difference 5. So they're both bigger than the current difference. The current difference, so the binary search gives us a current difference, right? And then we look around. Binary search gives us difference, and we basically look around. Whether binary search gives us a difference, or we're looking for the smallest. Well, I do think it should be binary search, so we make sure that the current step is the smallest. And then so we binary search first, and then we go like this. Expand up and we expand down. And then kind of just to see if the nearby will provide, and if the nearby provides better, then we just keep going. If the nearby already does not provide, okay, but it could be like 2 steps down, right? So it's like nearby does not provide a better approach. But this one, so like see this one we get a giant number. And then nearby, which increase this, but it should be whenever the difference between these is bigger than the difference. So that's when we stop the search. Right, so we go binary search first, we look around, and then until we find one that we'll keep looking, and until the difference between these two is bigger than the difference between the others. Because you have to notice, like most of the numbers, we won't have a lot, so we can probably afford this search. This one we're just gonna binary search, and then we're gonna just look on both sides. You know what? You know what? We're just going to search. Each number we're gonna search. Each number we're gonna search. That's gonna be O(n) squared. Like, I don't think we can afford O(n) squared. Yeah, O(n) squared though. Each value is 2, so for each layer we're gonna do 2 search for the odd number, and then for even number maybe a little bit more. That's gonna be 2 search plus this plus this plus this. Maybe I can do a search. Maybe I can just do a search. Do a like Hard search. Worst case scenario with TLE. If we TLE, we look for the answer. Alright? This is not correct, but we can improve. So we're gonna do range. Right? We're gonna do range. So we are going to do range. How are we gonna do range? Are you going to append something? I'm thinking. I mean, we can do. Oh, we can do another one. And this F00 for range. Like that. And then we can set DC probably in the size. That is fine. DC this minus 1. That's the last one. Last one. DC as the last one, and then we have this, this. How do I mute it? I actually don't know how do I mute it. I'll be back. Alright, I am back. Let's keep hacking this thing. We decided just to loop through everything. So we say this is the last one, and then we need to initialize the last one. So it's gonna be 4 number in numlist ct. I think we use this minus 1. We actually need I enumerate. Minus 1 I equals and okay, so we're not going to do any of these. We are going to just run this, and I'm going to print. See, what do we have? We have 39, 39, 78, 78, 66, 66. Yep, that is what we want, right? That's what we want. And then we can say for this, for I, and now from this position, from which position? From this position on, we're going to say for J and we're going to for K in for range, right? So we have for range, mean, range, now in dt I plus 1, right? I plus 1. I plus 1 is this, and for each one, and then I'm going to say if n is this number, if n is smaller than r min, so we probably need to get temp min, temp max equal, let's say, temp min, temp max equals n, then for n smaller, if n is smaller than temp min equals temp min, temp max equals then temp min has to be changed, temp max, r max. Alright, now n is not larger and equal to this, so elif n is smaller to r max, then P min, P max equals r min, r max, and else is if n is larger or equal to r max. So actually, we're going to put it here, so it'll be n is larger than r max. Then P min equals r min. And we go through each one of them, then we need to update, right? We need to update. So basically, how do we update? I do think if we want to update, that's actually not the right logic. For each one, we go through, we have a range, we have this one, we have a range, and with the range is just by myself, and then it's time we find a new range, so it's not going to be my n, like where my n looks like. It's going to be the temporary range. So I have a temporary range. And we use my range compared to your range. Right? My range compared to your range. That's actually not how I imagine it to be. So if I have a temporary range, so after I completed the first one, and we have a range, and then we will complete the second one, basically what we're trying to do is to find, so among all these ranges, we need to find a range that is the smallest when including me, So we're given a range and me, and then I can find a new range, right? So and find a new range that includes me, and find a new range. So it could be the same, right? It's here, it's here, it's here, and we generate a new range after this. And then, after this, we'll generate another range. And then the two ranges, we need to compare which one is bigger. And then we store the one with the smaller. Right. So that is how it's going. So basically, we are saying that so I think this one has to be inside. So every one, like, and then at the end, we're gonna get and then we say if Tmax minus Tmin is smaller than previous. Alright, so we need a yeah, we go through each one of these and then we put myself in it. I put myself in it. Okay, so this. We can say it's basically dpi j equals this. And then it's smaller than this and equal than for this. Yeah, I can simply say here dpi j equals math.in and minus math.in. I think that's fine. I'll work. And then we are going to, I think I'm going to do it. We just need the range to be the maximum. So it's 0, and we say 10 to the 0 and math.in, right? And then if my current value is smaller than RMA, and I want to say if R max minus n is hold on. How do we do this? So basically, we go through this and try to find one the minimum, right? So if this is smaller to dpi j 1 minus dpi j 0, then dpi j equals n r max. Well, if it's smaller than this, and then we say if r max minus r min is smaller than this, and this one is r min r max. Otherwise, we say the same thing. If it's going to be r min and minus n minus r min is smaller, so it's smaller in a crucial one with a smaller difference. Then equals r min, and this one will be 10. Right, so for each value in this pair, I'm going to put myself inside, and then we're going to find out and we're gonna find out smaller. I'm gonna find out the new range, and if the new range is smaller than my current range, then my current range will swap to this new range, and then we go for the next one and then see if it's going to be smaller. So if it's not going to be smaller, then we don't update. We go through everyone, and then after we go through every one, the front, then we have the range to start with this. So we're going to return the main value, 4. So we're going to go 4. This is 0 for range mean, range max, and DP 0, right? And DP 0, and DP 0 is this. So for each one, right? And then we're gonna say R max minus R mean. And we pass. So this one we pass. I mean, of course we're gonna pass because we are ranging through every single one of them. Oh, the first one failed. What the heck? First one failed. Answer 3, result 4. Alright, I think it's time that we need to print out the GP after every iteration and kind of check. Alright, we start with 3, 3, and 6, 6. We have 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. And then after the first round, second round 5 and 3, 3 and be 3, 5. That'll be 3, 5 and 5, 6. So okay, 5, 6. 10 will be 3, 10, 6, 10, and this going to be 6, 20. That's correct. The next one will be 5, 10. So 5, 10. We are going to go through 5, 10. Like the 5. 5 go to 5. 5 go to this. It'll be 5, 10. 5 go through this. It's going to be 6, 10, which is up. It's going to be 5, 10. And then 10 is going to be 6, 10. Instead of 6, 5. Okay, this is also correct. Next one, 1, 2. So for 1, 2, so 1 will generate 1, 6. 2 will generate 2, 6. I think this is where we got a problem. 2, so the answer is 2, 5, 3, right? Which will result in 3, which means for 5 it is 5, 6. So for 5 it will be 5, 6. Yeah, 5 is 5, 6. But 2 is not 5, 6. 2 is not 5, 6. 2 is actually 5, 3. So this is actually 2, 5. Which means on this 5, I should collect 3 instead of 6. This method doesn't work either. No, this method does not work either. Because we collect, because for 2, I look at 5, and 5 will decide on 6. 5 will not pick 3. So for 2, I wanted to pick 3. a sort won't work. Will it? If I sorted it, then it will become 1. Wait, like how do we sort? We sort based on the smallest value. 0, 1, 2, 1, 2, 4, 3, 6, 5, 10, 5, 10, 20, like that. We're gonna pick 5, 5. And this one will pick 3, 5. And this one will pick, this one will be 5, 5, from 10, 10. And then this one will be 6, 5, 6, something 3, 5. And this one will pick 1, 5, 2, 5, 3, 5, or 4, 6. 3, 5, or 4, 6. The same thing. Which means we don't care. Well, let's just say we pick 3, 5. I feel like this is another way. Okay. I am going to take the hint. Let's take more. More value for each number. It's only multiplying with a 2. Assume you start from the minimum possible value. Okay. If there is a better solution than the current one, you must have either a maximum value less current maximum value, or the minimum value larger than the current minimum value. So we go from the minimum. So when we say is everybody's minimum. So minimum will be 1, 1, 5, 5, 3. Right? That's the minimum of everybody. And there is a better solution than the current one. So the current solution was 4. If there is a better solution, then it must have either its maximum value less than the current maximum value, yes, or the minimum value larger than the current minimum value. Well, I mean, we start with the smallest, so it can only go up. So we just say current min value is 1, current max value is 5. So we just see if it exists. So current value is 1, 3, 5. So do we have a value who, when we double it, is smaller than 5? And the answer is yes. This double it is 5. So we can double it to 2. So now, like all the mean value, we have to go all the mean values. Mean value is 1, so we need to improve on the mean value. So mean value, so the 2 mean value, double it is 2, which now gives us a mean is 2, max is 5. And then say if we can double again, but we cannot because this is the maximum. So this will reach maximum. This one cannot change. This one cannot go anymore. So when they remove it, not remove it, we just lock it. So the mean value we cannot continue improve. And that's it. We're done. So the mean that I cannot continue improve. Okay, I kind of see the I see it. I see it. We might be able to implement something. Yeah, the DT is not going to work. DT is not going to work. I'll write about this example. The DT is not going to work. So minimum, I can call it minimum. Numbers in a score equals n minimum. If n is even number, num 10, n well, while so that's the same. And then num 10, all that's different. Num kind of yeah. And then let's say I also need a mean and that and equals minus and then time and say min equals what's the we can do it in one line. Min okay, so we have min max and we have the current, and then we just say if how do we know the limit? So we say is fine if any one of them can improve, right? If they cannot improve, how do we know if both can improve? I just have to go through. We need to know the position of the mean value. We need to know the position of the mean value. We need to know the position of the mean value. Well, then there will be new mean value, right? Okay, I double it. Okay, I have the mean and max of the current mean and max. And then if the current mean times 2 is smaller, then we try to see if we can improve it. And then as we are improving it, we're also looking for new mean value and new max value. Yeah, we're looking for new. What if I double it and then just like slightly above it? No, it's a difference, right? It's a difference. So we multiply by 2. So we have a mean and max. So when the mean multiplied by 2, if the mean multiplied by 2, the result, and it's larger than the current max, but the difference is smaller than the current, then we do it. And we also upgrade. And also, we do not know. So like if we double it, then the mean value would change. Either be its maximum value less than the current as a there is a better solution than the current one. It must have either its maximum value less than the current max value or the mean value larger than its mean value. Either its maximum value a better solution than and either has its maximum value less than the current value, yes, or the mean value larger than the current mean value. I think increasing of this, it's not decrease current max value, so we can only increase it. Multiply the current mean value by 2, and then see if it's a better solution. And then if it is, then we keep find the current mean value and multiply it by 2 until we cannot do this anymore. Right? So this is like the minimum. Alright, and then if there is any better solution than this, then the better solution, either the better solution's max value is larger. No, better solution's max value is a little smaller than the current solution's max value. All the current the max solution's mean value is larger than the current mean value. Right? Is larger than the current mean value. So with the current mean value, it's double. And after doubling, we compare, and then so we compare. So basically, for each round, we're going to multiply the mean value and see if we can reach. So each round, we're gonna multiply the mean value by 2, and it also has to be odd. If it's even, we cannot multiply. So we multiply 2, and then see if it's better. Record it, and then find a new mean value and new max value, and we're gonna stop when we're going to multiply it, and the mean, we have to find the new mean value, and that will shrink it. Yeah. So we have the mean value, and so we're gonna say well true, right? And we're gonna say and try and multiply current mean value by 2. This mean and is then we just return max and minus min. There's no way. Right. So if it's not, then we're going to say for n in I n in numeric and then right, if n equals min n, n equals min n, and 2 times n is smaller or equal to num I, then num I equals to. Actually, I think it's going to be like this. If else and break. Else, that means min cannot be multiplied by 2. Else, then just return n minus min n. That means the min n we cannot multiply by 2. And after we finish updating, so we need to find min n max and equals min num and max num like that. But it says fail. Oh my god. My goodness. This is ridiculous. I don't believe that I still cannot solve it. This is right. Come on. And let's check min and max. Min n and max n is 1, 5. Good. And if it's not, so we're actually doing it. N equals min n, yes. And then we check 2 times. Ooh. We can always times 2. We can always times 2. You don't have to check. You don't have to check because we already checked the mean. Yeah, if it's this, yeah, you always you can times 2. There we go. Now we're passing. Ah, man. You are kidding me. Alright, what is wrong? 1, 3, 39. And 1 times 2. Yes, it can, so it's 2. As most possible 3. That's correct. That's 3. 3, 6, and 12. So the smallest times 2 And then we're picking 2, 3. No, we can keep multiply. So if if this is actually we shouldn't do it here, right? If everything equals n, if min n is odd, like always, if min n is even, or 2, that's actually n. If n is even, n is odd, we multiply, or n is even, and we just check 2 times n is smaller equal to num I, else when returned. So which means we cannot. So which means it's an even number and it breaks. So we're gonna return min max n minus min n. Then we pass, right? And I do think we can make it faster, but I don't want to. I just want to get a pass. Pass everything, submit it by probably going through, let's see if I still have, yes I do start. Alright, run code. Alright. Submit. Oh, come on. Come on. Come on. Yeah, probably failure. Huh. Yeah. Oh, that's such a simple test case. What in the world? Expected 1. Oh, I mean, as long as I can multiply by 2, it doesn't really matter if it's even or odd. Yeah, it doesn't matter if it's even or odd. As long as I can multiply by 2. That is not correct. If this is mean, and if I can multiply by 2, then I multiply it by 2. And if I cannot multiply by 2, the mean cannot be improved, then we fail. If it's an even number, can I continue multiplying? I can. If okay, it's actually not like that. If I multiply by 2, so if it if it's an even number, then I can always, yeah. If it's an even number, if it is an even number, then I can always multiply by 2. So this will cause the last one. So because it's an even number, I multiply by 2. So if it's an even number, and uh, even number. Wait, I can always multiply by 2. So I can multiply by 2. Why do I have a result as 4? If it's even number, I can always multiply by 2. Because if if it's odd, I can always multiply by 2. Because if it's an odd number, I can always choose to multiply by 2. On an even number, I can only reduce. Oh, what went wrong? Oh, we need to record. We need to record. Don't bother. Yes. Let's do until we cannot. Yeah, else I'll just break it. Rest equals new. Rest max and then yeah. Oh shit. The hell? I stuck at 6 or 10. Yeah, why would I say break? Fall or I fall? Why would this still be stuck in here? I have no clue. I said yes, and then num should be 5 and 6. And then say if it's 5, let's find it, and then multiply, it becomes 10, and then 10 is not come out, and then done, come back up for, oh yeah, it does. So how do we end this loop? When the if n equals this, and then we get we break this. Oh. No. Else continue. No, not continue. I need a flag. All right. So the only difference is let's give it a fly. All right. Well, actually, there's quite a lot of difference. This is taking a long time. All right. Let's hope this one will do. Nah, it looks to me it's gonna be CLE. It's CLE. All right. Apparently, I know that we can improve for sure. Okay, so I think what it's trying to say is we need to make everything the most optimal. So we're gonna go math.in minus math.in please, and then just be a little bit more courteous. So we have this. Then Fn is going to this. Um, yeah, I think we'll just do this along the way. Let's see. If we do it along the way, I think it will be faster. Oh man, goodness, what is the matter with you? Are you saying this is not the same? We're going through num, right? We're going through them one by one, and we're trying to find, priority queue, priority queue, priority queue. Keep put. And we just need to keep track on the map. We don't have to track on the mean. We only need to track on the map. Alright, and then the result will be 0, on the top, that's the current smallest value. And then stable or true, doesn't matter. We're not gonna do this, right? Apparently, we're gonna pop it out. So we're gonna pop out, and then that time we pop out, that's current mean, we multiply it, and then we have the current mean value, and then we just keep popping until, so we pop it out, right? So current mean value, we popped out, and see if we can multiply it by 2. See if we can, and we multiply it by 2, we'll push in, and then we'll pop the next one out, and it's still current mean value. So just every time we just keep popping out, so we keep popping out the current mean value, and we see if we can multiply by 2. If we can multiply by 2, we do it, and if it's smaller than the current max value, then we don't care. We push it back into the heap and then pop the next one out. Every time pop out, we update our rest, and if it's, then we update this until we pop out the mean, and we cannot. Okay, so I think we can do this. So I actually want to go back to well too. Current mean equals heap q dot heap pop. If current mean is odd, then we can current mean times equals 2, and then max n equals max n current mean, right? So let's update max, and then 1, we do this. So current mean when it comes out, so current come out, rest equals mean, rest, current mean, no, current max minus current mean. That means we actually can do this to max value, right? So it's infinite. Then find the min value. So we pop out. So this is the current range. And then if it's 2 or 2 times current mean smaller or equal to, and is required when we push, and to push 2 things. And enumerate num is there. I want to push n I on plus, and then current mean I equals this, and then the result, update the result, and then it's current mean can multiply by 2 or 2 times smaller than this, we upgrade it. Alright, upgrade for this 1 times 2, and then when do we update the max n? The current mean times 2, we push it in, right? If we can, if we cannot, then if the max n thing. Right. So the max n. So let's if my current min pop out, and then we say it can times 2, so times 2. If it's smaller, it doesn't really matter. If it's bigger, if the current min times 2 becomes bigger than the max n, do we count it? Yeah, we can count it because it will not matter. Max will be this, current min will be this. This actually be bigger, so it doesn't really matter. Yeah, I think it doesn't really matter. And if else, which means the current mean cannot be improved, then we break. And we return the rest. Index out of range. Oh, wow, PP? The exhaust PP? Okay, something is not right. Oh man, the humanity. Alright, can we print here? Yeah, I can print it here. Let's do this. And afterwards, we can print PQ. So I'll pop this one out. We pop 1 0 out. Pop PQ and then we'll do rest. So I pop this out. So current will be 4 because max is 5, current is 1, and 4, understandable, and then 1 times 2. So, oh, I think I pushed it wrong. It didn't push it. Yeah, it didn't push it. Current mean times 2, and PQ dot push 2. Alright. Don't work. Yes. See, we failed earlier. Yeah, we cannot even, but I have high hope on this one. Actually, I don't have any cover. So only this line, submit, 13. Yes! Yes! We finally got it. Oh my god. Oh my god. My friend, 2.5 hours. If this question is not hard, I am going to hit my head on a piece of tofu until my head becomes red. Because this is ridiculous. It takes a ridiculous amount of time. It had a lot of issues going in. Yeah, we actually going to make it look nicer. So we do some lines, and then we are going to read. Uh, oh, let's write about it first. So apparently, I wasn't able to solve this problem on myself. I was thinking about dynamic programming. It's a DT. I was thinking of DT in the sense that uh, at each position in num we can expand, it. We can expand all the choices. We can expand all the choices, and for each number we pick the best uh, possible path onward, and if we work from the last position back to the front, then we will have the best option calculated at the front. Now this was my thought. For instance, I need to. This is the wrong idea using GP. For instance, given 2 and given 2 and 8, I can extend it to 2, 1, 2, 5, 10, 1, 2, 4, 8. So I would go from the position 1, which is 5, 10. For 5, the best option is 4 in the final, and it's in position 2. So I record the mean difference going from 5 to the last position at 1. 10, we use 8, so the mean shift to 10 is 2. Then we work on 1, 2. For 1, we choose 5 and always give 4. So and give 4. For 2, we also choose 5 with give 3. So give max 4, 1 equals 4. 2, that's 2, and that's this. Max 3, 1 equals 3. So the final answer is the mean of the diff in position 0, which is 3. Now, this DC idea doesn't work. A counter example is 4, 12, 3, 12. You can try it yourself. So basically, this problem is not sub. This problem cannot be approached with DP because the subproblem is not completely dependent on the problem is not completely dependent on the optimal solution of subproblem. I eventually have to get the hint which pointed out that I shall find the mean possible values at each position and incrementally double the mean value. Incrementally double the mean value and we compute the overall diff until there is a mean value that cannot be doubled. It works because, as the hint points out, if the current solution is not the optimal, then we must have the optimal solution with its mean value mean value larger than our current mean value. We also need to use PQ to illustrate the searching of the mean value. So I think it's O n log n because this is O n, and then this, depending on how many iterations you want to go. In the worst case scenario, you just have to go through every one of them. So in the O n log n, our runtime clock at 1068 milliseconds, which gives us 35% ranking. Alright. Okay. Black. Impossible value. And therefore, under index. for the you know, update current the criteria for determining whether the current name can be doubled. It is up to doubling it is still it is even, and doubling it is within the limit umbral. Hey, alright, it's long enough for today, so I think I'll go through the discussion myself. I don't want to waste everybody else's time. And I'll let you know tomorrow if there's anything interesting that I find. Actually, I think it's similar solution. It's most likely probably we got it wrong, but yeah, we'll see. Alright, I'll see you guys next time.